Just getting a periodic table here because we'll need to reference that a bit today. Okay, we don't need that right now. So when it is here, I need it to be behind me a little bit. Okay, there we go. So now I've got a nice periodic table behind me here. Turn that off for now. Okay, well, we'll get started in a couple minutes. Everything seems to be working properly. And today we're going to talk about subatomic particles. So it looks like we've got a couple people in here. We'll wait a couple more minutes in case anyone else wants to join us. There's my reminder to start. Okay, I think it's time. Well, good evening, everybody. Happy Thursday evening. Hope everything's going okay. We're going to work our way through some of this stuff about subatomic particles that you'll see in this third packet. As usual, I'm going to pause and ask questions and ask you to respond. You don't have to, but this works better, especially if you're used to a more live class, if you can participate. And it'll be a good chance for us to check how you're thinking and make sure that the things are making sense. As usual, if you have any other questions or other concerns that you want me to address, please add them to the chat. You can use the YouTube chat or Discord under the live events channel, or the live streams channel, sorry. It does seem like for most people the YouTube chat is a little bit quicker, but I think that could have just been that one day, so I don't know. All right, so let me know if you have questions. I've got the chat open, and I will be keeping an eye on it as we go through this stuff. Okay. So in this next section, we talked last about matter and physical and chemical changes, and now we're going to zoom in a little bit and look at the atoms themselves. So we talked about elements being made of a particular type of atom, only one type of atom, and now we want to know, well, what does that mean? What makes an atom a particular element versus a different element? So some of this history, you can read through that. I don't think I need to address that, just kind of how this stuff got discovered, what kinds of experiments were done. It's interesting if you got a chance to take a look at it. There are some good videos online about the types of experiments that these people did back, quite a long time ago when it would have been fairly difficult to determine these things, and they were able to do that with the technology of the time. All right, so here's our model here of an atom. So you may have seen something like this before. You've got your nucleus in the middle and some things going around the outside. Based on our key here, we can see that inside what is called the nucleus, we've got protons and neutrons. So the lighter colored spheres here being the protons, the darker colored spheres being the neutrons. Uh-oh, Alyssa says it's cutting out. Anybody else? Is it cutting out for you? Are you having trouble understanding me? It could be my connection as well. Can anybody else confirm? Is it something happening with the audio? Okay, Alyssa, I think it might be your device then. Let me know if you think it's something on my end. Okay, so looking at this model, we can kind of count this, assuming we can see everything. If the neutrons are these darker spheres, I see 3 of them, and I see 3 electrons, and I see 3 protons. And hopefully you can see that as well. The center of the atom we can see are the protons and the neutrons. And the dense part is the nucleus that contains most of the mass. So what does that tell you about the masses of protons and neutrons as compared to the mass of the electrons? Well, the mass of the electrons is much less. Much, much, much less. Electrons have mass, but they have so much less mass than the other particles that we can say that they effectively have no mass, even though they do have mass, but compared to the others, it's just so small. Which particle do you expect to be easiest to remove? Anybody want to give that one a try? If you could pull one of those particles out of the atom, which do you think would be the easiest to pull out of the atom? Electron? Yeah, electron. And you can kind of see why that would be, right? Because it seems like it's kind of over on the outside. There is attraction, but we'll get into that more later. So this is a really interesting question, I think. What is between electrons in the nucleus? So you've got the nucleus, you've got electrons. What's in between? Any ideas? Like what's like here? So we have a guess of nothing. Yeah, exactly. Nothing is there. It's space. And this distance is actually pretty far. You could fit many, many, many nuclei. This is a condensed picture, but you could, in reality, you could fit many, many nuclei between the nucleus and the electron. So what that means is if you look at anything, any matter, it is mostly nothing. It's mostly made of nothingness, of empty space. So think about that next time you're on like a bridge or something. That below you is mostly nothing. Okay, so let's look at the particles individually, their charges and their masses. And one way to figure this out is to kind of look at it at an example. So you can see here we've got a picture of 3 different atoms with 3 different masses. And we're going to measure those masses in what we call atomic mass units, or AMUs. So atom A, we say its mass is about 1 AMU. Atom B, it's about 2. Atom C, it's about 3. And let's summarize this and then think about the masses. So atom A, we can count these things. It's got 1 proton, no neutrons, and 1 electron. Atom B has 1 proton, 1 neutron, and 1 electron. Atom C looks like it has 1 proton, 2 neutrons, and 1 electron. So then if we were to find the overall masses, remember the mass is given here. So 1, 2, and 3. So if that's true, and a proton has about a mass of 1 AMU, what do you think, like based on atom A, what do you think the mass of an electron is? Obviously, these are pretty small numbers. We have to assume it's about 0 AMUs. So it's true that an electron has mass, but its mass is so little compared to the others that if we standardize this AMU on the proton or the neutron, the electron effectively has no mass. All right, so that neutron, again, we can say has about 1 AMU of mass. The other thing that's given here in this particular model is that the overall charge for all three atoms is 0. Okay, so the charge would be the balance of positive and negative charges. And I think we were told earlier, I think I skipped over it, but the proton has a positive charge, and the electron has a negative charge, and the neutron has no charge. So each electron, we're going to say, has a charge of -1, and the neutron is 0. If it were possible to add another neutron to atom C, what would be its approximate mass? So it would go up by 1, right? So atom C would become, the mass would be 4 if it had another neutron. And how would the electron change its mass? It wouldn't, right? So let's summarize those up. Actually, you know what? I'll let you do that. I think you can probably do that. So based on what we found, what is the mass and the charge of each particle, and where do you find it? In the nucleus or out of the nucleus? All right. So now let's flip over to the periodic table and think about that a little bit. So I'm going to pull up my periodic table behind me here. All right, here's my periodic table. So if we were in class at Harper, I could just sort of point to it on the wall, and you'll have seen it, every day all year. But we're not there, so I don't know how much you've seen a periodic table. There is one. You did see the one in the classroom when you came for lab, probably. But we're going to look a little bit about the organization and specifically what information we get from a periodic table like this one here. So you can see first that the elements are arranged in increasing atomic number. I don't know actually how well you can see that periodic table behind me, because it kind of depends on your screen size, but you've probably seen this before. The atoms go from 1 up, and so like they count each time. So hydrogen is up there as 1, and then you go to helium as 2, and then lithium 3, beryllium 4, and now we got boron 5, and carbon 6, and 7, 8, and so on, going across. So that's called atomic number. If you have a periodic table handy, you might want to pull it out to look at as we switch back and forth between the document and the periodic table, but I'll also try to switch back and forth as best I can. All right, so back here to our notes. Atomic number is defined as the number of protons each atom in that element has. All right, so number of protons. So atomic number is number of protons. Excuse me a second. Sorry. Atomic number is the number of protons. And if that number somehow changes, we have now a different element. So if we go back to the periodic table here, each element has its own atomic number. The atomic number is the number of protons. So if the number of protons changes, then the atomic number also changes, and therefore the identity of the element changes. So the thing that separates one element from another is the number of protons, and just the number of protons. So you can keep that in mind when we think about like later on we're going to look at particles that have, atoms that have different numbers of the particles of protons, neutrons, electrons. And so you can think about what ends up affecting the identity of the atom when we actually change the name and the symbol. And that's when we change the number of protons. The reason there's a comment here, this is easier said than done, is, let me flip back, is because when we do chemistry in the lab, we never mess with the numbers of subatomic particles. We never mess with the number of protons, at least, just electrons. So to do that, you really have to do nuclear reactions, which is a whole other thing. Okay, so you can look at your periodic table and find some that have some different letters and find those sorts of things. And what this really talks about here, the most common elements found on Earth, is what's the name, what's the element symbol, and then if we look up the atomic number, that's also always going to be the number of protons. So these two columns should always be equal. So whether you know the atomic number or you know the number of protons, you always have all this information as long as you have a periodic table. Oh, thanks. All right. And so then the other thing we need to watch on the periodic table, for those of you who haven't used it much before, notice that there are a few elements that have only one letter, like carbon, nitrogen, oxygen, phosphorus, sulfur. And all the rest of them have two, and they're identified by two letters, an uppercase and a lowercase. So if we look over, I don't think I can get my finger that far. Close. Yeah, right here. So this is cobalt, CO, and that's capital C, lowercase o. If we write CO, capital C, capital O, that's going to cause some confusion because capital C is carbon and capital O is oxygen. So we're really talking about now a compound between carbon and oxygen, and that one actually has a name. That's called carbon monoxide. So making sure that you make a good difference between the capital and the lowercase letters when you're writing elements is important and can lead to some confusion if you don't. All right. So I've got a blank periodic table for you here, and we won't go through this right now, but different columns have some different names. And we're going to refer to those names, so we need to kind of know what we're talking about. In my periodic table here, whoops, got the wrong thing up here. Pull that up again. Okay. You can see those colors. So we've got way over on the far, I have no idea what this looks like to you, but that's left to me. I don't know. Yeah, I guess it would be left to you too. So on the far left, we've got the alkali metals in kind of pink with a stripe. And then next to them, the alkaline earth metals. Right in the middle here are the transition elements, or transition metals, sometimes they're called. Then we've got the other ones that we're gonna be concerned with. Behind me here are the noble gases all the way over there, and then the halogens. And we won't really talk about the special names over here. I can't even really see what my periodic table says they are. Then we've got some metalloids kind of in between the metals and the nonmetals. But you can find this on any periodic table. And again, you don't need to memorize those names. You'll see those on the periodic tables, but we will go over them a lot. So it is, you probably will just have them memorized by a couple weeks from now, just from going through and doing stuff with them. But one way to learn those is to just pick some colors and color them in down here. If you don't have colors, or you can't see colors well, or you can't see colors at all, you could use different patterns or things like that also. One important distinction besides those groups is where you see this little staircase here. We're going to generally say that metals are found to the left of that and nonmetals are found to the right of that. Now, there are some exceptions here. Primarily the elements that go right along here, which, let me pull that back up here. So you see that like the elements right along that staircase, with the exception of aluminum, those are called the metalloids or the semi-metals because they're kind of like metals and kind of like not metals. So once you have those known, you can look up some symbols and some names and place them in their families and groups, and I'm sure you can find those on your own. We should probably also stop for a second here and say that what is it that's the difference between a metal and a non-metal? Why do we care so much about that distinction? From a chemistry standpoint, the way the electrons work in those is very different, and we probably won't get into that too much in this class. But just physically, like, you know what a metal looks like, right? Like, it's just instinctive. It may be hard to describe, but you know, like, if you encounter something, you can probably figure out it's metal. Can anybody add something in the chat? Like, how do you know something is a metal? What is it like? What is a property or a characteristic of a metal that tells you that is a metal? Anybody have some ideas on that? Nothing? You know what metals are though, right? I mean, not from a chemistry standpoint, just from like a life standpoint. Like, you know what something metal is like? Heat conduction. Yeah, I like that. So metals conduct heat really well. If you, the chemistry word for that is heat capacity. They have a very low heat capacity. Actually, no, that's not quite true. Heat, thermal conductivity is different from heat capacity, but similar idea that it doesn't. It's easy to heat up metal. It doesn't take a lot of energy to raise the temperature of metal. That's heat capacity. And then also metals conduct heat along their surface or through their bulk very easily as well. If something, if you've got a pan on the stove with a metal handle, you can't touch the metal handle, you'll get hot, or you'll get burned, right? So heat conduction is a good one. Other things are things like it's shiny. It reflects light in a very particular way that we often say is a metallic luster or a metallic shininess. Also, metals, if you hit them, if you put a lot of force into them, they can dent and they can bend. The terms for that is malleability or ductility, that they can be hammered out or pulled into wires, whereas nonmetals tend to be more brittle, where if you smash them, they fall apart. If you hit them really hard, they fall apart. And those actually are all consequences of the electronic structure of these things, going down to the atomic level. But we, for us, we just want to kind of recognize that there is an important difference between metals and nonmetals. The other big one, of course, is electrical conductivity, that metals conduct electricity, like wires are made of metal, and nonmetals don't conduct electricity. Again, in general, there are plenty of, there are polymers made from carbon that conduct electricity. Graphite is a type of carbon that conducts electricity, but in general, metals will conduct electricity better. Okay. So now let's look at what happens when we start changing those numbers of particles. So I've got this model here. Model just meaning something that is meant to express reality but is not actually what the reality looks like. So we're talking about some different ions and atoms here, and we're going to express their subatomic particles with little circles of different types. In this case, the nucleus is represented by the protons and the neutrons. On my copy here, it's a little hard to tell the difference between the proton and the neutron, but we know the neutrons are in the nucleus, so we can tell. So we got the protons and the neutrons in the nucleus, and then we've got the electrons coming around on the outside. And just with this information here, we should be able to make some distinctions about some different effects of these differences in subatomic particles. So let's take a look at some of the information here. 1H, 2H, and 3H are isotopes of hydrogen. So let's just stop there. We'll go one more sentence. 12C and 13C are isotopes of carbon. Let's think about that word isotope. Okay, so if we are saying now that these first three blocks of hydrogen are isotopes of hydrogen, and these first two types of carbon are isotopes of carbon, what is it that makes atoms isotopes? Can you figure it out from there? If we know that these three are isotopes, what does that tell us isotopes are? How does that help us define isotopes? Throw out an idea there if you can. What do you think is different about isotopes, and what do you think is the same about isotopes? Yeah, different number of neutrons. Exactly. And so if, I assume you figured that out by looking at these pictures and recognizing that the only difference is the number of neutrons. So this one has 0 neutrons, this one has 1, and this one has 2. If those are all isotopes, then isotopes must differ in the number of neutrons. Okay, if we look at these two carbons, same thing. Now we can't really see all the neutrons, but we've got some help here in the thing. So it says 6 protons, 6 neutrons, and over here 6 protons, 7 neutrons. So again, only differs by the number of neutrons. So that means that the number of protons stays the same, and that in fact is the definition of isotopes. For isotopes, you need to have the same number of protons, so it's the same type of element. That's where that term isotope comes from. Iso means the same. So isotopes have the same identity, it's the same type of element, but they have different numbers of neutrons, so different atomic weights, different overall weights. You'll also notice here that we've got some more decimal places. So when we look at our atomic masses and atomic mass units, you can see that it's not really exactly that number. It's a little bit different. And this one actually is exact because carbon, we actually base our whole AMU system around carbon-12. So we set arbitrarily carbon-12 is 12 AMUs, and then we find everything else from there. You don't have to do that. I mean, that's how those are calculated in general. Okay, so seeing that, you can probably work your way through the rest of these, looking at what these different elements have in common. So let's look at the, we already talked about this. What's the significance of the atomic number? Of course, that's the identity of the element. You can also probably figure out now that these little numbers on the upper left of the element symbol correspond to the atomic mass. So that's going to be the protons and the neutrons. One thing that we do want to be clear about, though, is that these atomic masses, or mass numbers, sometimes we'll call them, are not on the periodic table. And this is a common source of confusion. So let me see if I can maybe zoom in on this a little bit. I don't know how far I can get, but yeah, that looks like about as big as I can make it. So let's see, what number can we see easily? Well, let's look at carbon right here. Oop, my finger doesn't go up that high. So carbon up above me there. You'll notice on the periodic table it says 12.011. But of course, if we go back to our model here, we actually have two different types of carbon listed. One is carbon-12 at exactly 12, and carbon-13 at 13.0034. Neither of those is 12.011, which is what we see on the periodic table. And that's because these numbers on the periodic table are not mass numbers in the same way that we're talking about right now. These are actually averages. So in the world, there is carbon-12, there's carbon-13, and there's actually carbon-14 also. Most of the carbon, about 99% of the carbon in the world, is carbon-12. There's a little bit of carbon-13 and a tiny, tiny bit of carbon-14. So when you average all that together, when you average those abundances together, then you get 12.011. But the individual isotopes have their own individual masses. And we, even though it doesn't say on that form, on this worksheet, we consider those to be whole numbers for our purposes. So carbon would be 12 or 13 or 14. 14 is not listed here. All right, so in order to know the atomic mass number, this number that goes up in the corner here, sorry, my mouse is off a little bit for some reason, we need to actually know the number of neutrons. It's the only way you can get that number. You can't get that number from the periodic table. It's not there. It's something else. So as you'll see down here, near the end of this document, when we start looking at these overall differences in particles, you'll notice that none of these are totally blank, because we always need to know either the number of neutrons or the overall mass number if we're going to find the other one. So it's not something we can just look up on the periodic table. All right, so the last thing I want to talk about today is what happens when we change the numbers of electrons. So if we go back up to this model here, we can see we have the hydrogen, these three hydrogen isotopes that we just talked about. And there's also this hydrogen ion, and you can see that the difference between a hydrogen 1 atom and a hydrogen 1 ion is that this one is missing its electron. So no electron there. And that's indicated in the symbol with a plus here. So this is H plus, or hydrogen ion. Okay, moving down to the carbon, we see the same thing. We see carbon 12 and carbon 13, and then we see carbon 13 with a minus sign above it. And this tells us that there's an extra electron. So if we were to count these out, we'd see 1, 2, 3, 4, 5, 6 carbons, or 6 electrons here, 6 electrons here, and 1, 2, 3, 4, 5, 6, 7 electrons here. So changing the number of electrons changes the charge of that particle. And if that charge is not neutral, if it is positive or negative, like this one is -1, this one was +1, and then the magnesium down here is +2. So if it is not 0, then that is called an ion. Ion meaning not a charged particle. So electrons are negatively charged, protons are positively charged. If there's an equal number of protons and electrons, then we have a neutral atom. If it is an unequal number of neutrons and electrons, then we have a charged atom, and that's called an ion. So you'll see some of those over here in the questions, answering some of those things, and you'll get some practice with that in the homework this week as well, the Mastering Chemistry homework. All right, and then just another, I guess the very last thing before we stop. When we look at isotopes, there's a couple different ways we can write them. So we've seen this style right here, this 13, or the number to the upper left of the symbol. We can also write them in this way, where we write the name of the element and then the number next to it. So carbon 13, or just C12. This one's very uncommon. You don't see that quite as much. Well, I take that back. I guess in nuclear chemistry and stuff, we'll see that. These are all different ways of writing the mass number. Sometimes you might also see the atomic number written underneath. So like uranium's 92. So sometimes they'll write a little 92 on the lower left. That can be helpful if we're dealing with nuclear reactions when those things are changing, but it's redundant, because if it's uranium, we know it has to be 92. If it had any other number of protons, it would be some other element. And we look that up on the periodic table. So those are some different ways to see those. And then tomorrow morning at 10 o'clock, we'll come back, or I'll be back. I don't know if you will or not, but I'll be here, and talking about electrons, different numbers of electrons. And the goal of all of this, really this whole unit, is to be able to do this. Make this a bit smaller. So to say, all right, if you know the symbol, can you fill in all of these different things? Or if you know these numbers, these particle numbers, can you fill in all these different boxes? So just understanding what those symbols mean and how those apply to the different subatomic particles, that's really the goal of this unit. All right, so that's all I've got to say for now. Are there any questions or things you want to go over more tonight? Go ahead and leave in the chat or the Discord, and I can address them now. Can you do one? You mean on this, like on the table? We'll do it tomorrow, because we'll go through it tomorrow. Our exams, yeah. So let me actually pull that up, because I don't know offhand, but if we look at the syllabus, the exams are definitely on the calendar there. The first one is probably coming up. But let me just check this. Okay, so the first exam is going to be in week 6. So right now we're in week 3. So the week of September 28th, September 28th through October 4th will be exam 1. And that's going to be online. The way it's going to work is that it'll be posted on Blackboard so that you can do it at any point during a certain period. We have to kind of coordinate with the other sections how we're going to set that up, but it'll be like, it may not be the entire week, but it'll be at least a few days that you can take the exam whenever you can. And when you're ready to take it, you will set up in Blackboard to take the in Blackboard to take the exam. It'll be in Mastering Chemistry, and you will use this thing on Blackboard. I haven't tried yet, so I hope it works, called Honor Lock, that the college is using all throughout the college to do exams. And basically it just monitors your computer and your webcam and stuff and makes sure that you're not looking up answers or looking at your notes or talking to people or anything like that. So you'll do the exam online at home, but with some of this monitoring software. If you look at the schedule at the like the last page of the syllabus, you'll see the first exam the week of September 28th, the second exam the week of November 2nd, and then there will be a final exam at the very end of the course. All right, another question. The purpose of the section is to know how to properly fill in that chart. Yeah, I mean, to understand what the different numbers of, how the different numbers of particles, protons, neutrons, and electrons, affect the affect what's going on, affect what's happening. So the better you can do this type of a chart on your own, the better off you'll be for this section. And you'll see the homework follows that as well. So looking at like, what does it mean for things to be different isotopes? If I gave you two symbols, are they isotopes or are they ions or are they the same, or things like that. So yeah, does that make sense? Anything else? Okay, great. Okay, well, let me know if anything else comes up, especially since we're doing another stream right, like pretty soon, tomorrow morning at 10. If you want to send me a note in the Discord or an email or something if there's something you want me to address specifically. Otherwise, we'll just plan on talking about ions a little bit more and going through this table, and then talking about one more thing that isn't quite in this packet, valence electrons. So I'll see you in the morning. And if you can't make it in the morning, you can always watch later. And I'll see half of you on Wednesday in person, hopefully. So good night, everybody. Thanks for tuning in.